Hello, physics class. Hope you all had a good weekend. We're going to continue our discussion of electricity today. And I want to start off with what we left off with last lesson. And that is the conservation of charge. So I want to reiterate that electricity comes from electrons, okay? And electrons obviously are negatively charged. So in order for something to be electrically charged, it either has to have more electrons than it needs or less, right? And so it could be negatively charged or positively charged, right? But either way, electrons cannot be created or destroyed. They are simply transferred, right? They are a form of energy, and so charge is conserved. And let me kind of put it this way. If you take a comb, okay, let's see, I'll just try to draw a little comb here. This is a comb. Okay, and over here is some nice hair. Yes, okay. And I can't draw. All right, so we all know that we can create static electricity by running a comb through our hair. And this is kind of fun when we can actually do this live, but it is what it is. So what happens is the comb ends up getting negatives, right? So negatives go from the hair to the comb. So now the comb is negatively charged. And what happens to the hair? Well, the hair becomes positively charged. So no charge was lost. It was simply transferred. And that is the conservation of energy. Okay, so far in man and creation, we have not had any loss or gain of charge. Okay, we already talked about the fact that if there's an equal amount of electrons and protons in an atom, that we say that is that has a neutral charge, and if it has a negative charge, if it has more electrons than protons, we'd say it's a negative ion. Okay, and so let's see, adding electrons, okay, gives us a negative ion. And subtracting electrons, right, or losing electrons, meaning there's more protons. Protons don't get transferred. So if you lose electrons, you have a positive ion. Okay. All right. And then obviously a negative ion is negatively charged, and a positive ion is positively charged. Okay. Now, what they have discovered so far is the electron is the smallest unit of electricity. You can't have a half of a charge, right? It's either it's a whole number of electrons, okay? Now, what they did find out though is that charge is kind of made up of grains or elementary units they call quanta, right? So we say that charge is quantized, all right? If it, and we're using quanta as this unit, but really we tend to use electrons, okay? And we'll talk about that in just a little bit, right? So, when you scuff your feet across a carpet, the negative ions from the carpet are being pulled into your feet, into your shoes. So the carpet actually becomes positively charged, and your feet, your body actually becomes negatively charged, right? So that's why when you touch somebody else, what happens? Well, electrons are going from you to that person because charge always wants to be in balance. Okay, so that's why we get a little electrical shock, which, by the way, is also why you have to be a little bit careful at gas stations because even the tiniest electric charge can spark gasoline. So like, you want to make sure that you don't have a buildup of electrons. And one way to do that is to touch metal on your car, which is another reason why they say not to use your cell phone while you're pumping gas, because there's an electron flow happening with your phone. That was more the case with analog phones than it is digital phones, but still there is an electron flow. So just be aware of those things. Now, the cool thing about the electric force that we're talking about is the electric force actually behaves very similarly to the gravitational force, right? So the force of gravity was capital G and then M1, M2 over the distance squared, right? That was for gravity. Well, the electric force is similar, okay, but they use the K for the electrical constant, and then Q1 stands for the charge of item object 1, and Q2 stands for the charge of object 2, okay, but it's still divided by the distance between them squared, okay? So very similar. We'll talk about some differences. One difference is uh, with the electric force is you could have that this force can be attractive or repulsive, right? Depending on whether the charges are the same or the charges are different, right? So a negative sign will come into play there. Now, this formula for force was actually discovered by a gentleman by the name of Charles Coulomb. And so the units are a capital C, all right, and we spell Coulomb. Ooh, sorry, can't use my pen. We spell Coulomb like that, okay? So very similar. One other main difference is if you remember the gravitational constant, capital G was 6.67 times 10 to the negative 11, right? Well, K, by contrast, is 9 times 10 to the positive ninth Newton meters squared over coulombs squared. Okay. 9 billion. Okay. So K is very large. Now, it's a little bit misleading because where does electrical force come from? Well, it comes from electrons. Well, electrons are very small. And that's one reason why we have to have this K be so big. But it does also show us that the electrical force is quite a bit stronger than the gravitational force, okay? Now, it turns out that 1 coulomb is equal to about 6.25 billion. That's a lot. Whoops. Billion electrons. Sorry, I don't have my pen today. Okay, so 1 coulomb is 6.25 billion electrons. Now that sounds like a lot of electrons, and it is, but it's actually the amount of energy that it would take to light a 100-watt light bulb for about a second. Okay, now so it's something, but it's not as much as the numbers say. So it's all kind of confusing because we're dealing with these huge numbers, but they don't really amount to a whole lot. Okay. Um, Not much else I need to say about that. I think it is interesting that Newton's law of gravitation is so similar to Coulomb's law for electrical force, and they didn't even work together on them. Like I mean, it's kind of weird how that worked out as far as forces in nature. Okay. All right. So the next thing I want to talk about is conductors and insulators. I hope that we kind of have a good idea of what's a conductor and what's an insulator, but we're going to talk a little bit about it a little bit more in terms of electrons. All right. So if the transfer or the flow of electrons is what creates electrical force, then a conductor is something that allows electrons to flow fairly easily through them, right? So metals, for example, are good conductors. Okay. Why? Well, because metals tend to have free electrons, right? They tend to have a little bit of extra electrons. And so it's easier for other electrons to flow through that or to kind of bump other electrons down the line, if you will. Okay. So, and remember, we talked about the shells in an atom, right? Those extra electrons are always on the outermost shell. And so again, that what that does is that allows for the freedom of other electrons to move through them. Okay. Um, Expensive metals like silver, gold, platinum are some of the very best conductors, right? They don't corrode and all that, but they're very expensive. So copper and aluminum are also decent conductors. And the reason we use them is not because they're great conductors, but because they're cheaper materials. Okay, so when you're looking at wiring in your house or whatever, it's usually made of copper, but aluminum can be used also. Okay. However, the electrons that are in rubber or glass, things that are not good conductors, are tightly bound, right? There's not free electrons loose to be able to allow movement through them. And so by being tightly bound, electrons can't flow through them. And so what do we call that? We call those insulators, okay? So glass obviously is a great insulator. Um, Rubber, plastic, all those types of things. Um, and one thing that I don't know if you've ever paid attention, but like if you look at those large electric towers that carry the big wires, like from a power plant, they actually have a glass insulator between the wire and the metal tower itself because they don't want the electricity to flow into the tower, right? So they use this big glass looking almost like a slinky thing up there to insulate the metal from the wire, okay? Um, and all materials are either conductors or insulators or something in between, right? Humans, we are conductors of electricity. We're just not great conductors of electricity, but it can happen. So we're probably somewhere in the middle of the road there, right? So some materials um, are not good conductors nor good insulators. Germanium, silicon, for example, right? They're kind of in the middle. But by doing certain things to them, they can become excellent conductors or excellent insulators. Okay. For example, if you have these items in pure crystalline form, then they can be excellent conductors, right? But if you put an impurity in them, um, I'm sorry, let me back that up. By putting an impurity in them, it does make them great conductors because what it does then is it offsets the number of electrons that it has. Okay. And so then it can become a good conductor. So some materials that we say that can be made into good conductors or into good insulators, we call those semiconductors. They're not necessarily like in the middle of the road. They can be made to be good conductors or they can be made to be good insulators, depending on what we do with them and how we kind of change them a little bit. Okay, so a semiconductor is what that is. All right. If you've ever heard of the term a transistor in electrical talk, okay, a transistor is just a lot of semiconductors sandwiched together. Okay. They're used to control the flow of electrons in circuits, right? They can also be used to amplify radio signals and produce oscillations in transmitters. Okay. So a transistor, they might put that in an electrical circuit to maybe slow it down if it's a good insulator semiconductor, or they might be put in there to speed something up, speed the flow of electricity up. Okay. Semiconductors also will conduct when light of the proper color shines on it, right? So like if you have selenium, for example, it's normally a good insulator, all right? And so any charge that builds up on its surface will stay there for extended periods in the dark. However, if you then expose that same selenium plate to light, the charge will flow through it and leak away. And so you can take a semiconductor sometimes and make it into what we call a battery, basically a battery. Then it can, because it can hold electrical charge if it's being a good insulator, and then we change it by adding light to it and it becomes a good conductor. Okay. Sometimes we can take a semiconductor and put different patterns of light and dark on it. All right. and meaning that the dark areas would hold charge and the light areas would let charge flow through them, right? Or let, leak electrons, so to speak. And then if a black powder were brushed across its surface, the powder would stick only to the charged areas, okay, where that plate had not been exposed to light, okay? And this is exactly what happens in a photocopier, right? A photocopier uses electrically charged plates to, because we use black and white mostly. The dark areas get copied, the light areas do not, okay? Last thing is sometimes we have materials that really, really conduct electricity well when they are changed in a different way. And mainly that way is by making them really cold, okay? When a material has zero resistance to electrical flow, we call it a superconductor, okay? So a superconductor, has zero resistance. Now, there's not very many materials that are like this unless, like I said, we make them really cold, okay? This is what you probably heard of superconductor trains, right? And this is exactly what happens, okay? So they actually first discovered superconductors in 1911 when they took some metals and put them near absolute zero, okay? They also have taken now certain metals and put them at very high temperatures, like near 100 Kelvin, which is still cold, but it's quote unquote high when compared to absolute zero. They can make superconductors at high temperatures as well. Okay, we'll talk more about trains and high powered emission lines and things like that. But transistors, semiconductors, superconductors. Just kind of need to know about those things. If you didn't quite understand the whole photocopier thing, not going to be a big deal. We're not going to talk about it a whole lot. Just know that semiconductors are materials that can be made good insulators or good conductors, depending on how we change them. And that superconductors have zero resistance, but they need to be super cold or not super cold, relative to that material. Okay. All right. That's going to do it for today. I will talk with you tomorrow.